Throughout this unit, the ideal gas law, PV equals nRT, has been crucial in our understanding of the gases and, moreover, our understanding of how to manipulate the gases. And I've been especially compelled by the mathematical side behind the law itself and how this law came to be. In my research, I found many interesting and unfamiliar concepts and ideas which underpin this quite simple formula, PV equals nRT. So today I'll present my findings and hopefully you'll understand the how and the why behind this ubiquitous law.
So today we're going to prove the ideal gas law, which I'm sure all of you guys know as PV equals nRT. However, the majority of this video will cover another concept called U, which will provide us with the knowledge to tackle deriving PV equals nRT. Uppercase U is the internal energy or the total kinetic energy in a system. Before we start, let's make some fundamental assumptions in our scenario. Some basics include the mass is constant throughout. It neither increases nor decreases. The particles behave like ideal gases, but most importantly, the particles move along three axes. What do I mean by this? Let's visualize it. In a box, for instance, U would be the K total created by the vibrations and movements of all the particles along these axes. This is important because when we calculate the pressure of a single wall later on, we'll have to consider only the amount of particles on one axis. In this case, is this axis. This will make more sense as we work through the problem. However, we need to set this straight first. Also, for some basic notation tips, I want to point out the U or total kinetic energy is equivalent to the Ke of one particle times the amount of particles, which is denoted as the number of moles, N times Na, which is Avogadro's number. Let's move on to actually deriving U. So let's zoom in on the movement of one specific particle with a certain mass, m, which is moving at a certain velocity, v. We know that pressure is force over area, so let's find the two variables. Area is really easy to find as it's bumping into this cube's wall, which is x squared. However, deriving the force is a bit trickier because we have to also involve momentum. Let's take a step back. Force is m times a, where m is, of course, mass, and a is, as we learned last year, acceleration, which is just the change of velocity over the change in time. Knowing this, let's rewrite the entire force equation as the change in m times v over the change in t. This is where the momentum comes in. Don't worry, all you need to know for momentum is that it is mass times velocity and represented by p. So saying this, we can replace the numerator of the force equation, the change in m times v, with the change of momentum, or p, all over time. I know this might be confusing, but bear with me. Let's return to our visual here. Our job now is to find the change of momentum and the change in time in order to find the force which we'll use to derive the pressure. At first, we're saying the particle will collide with the wall. Boom. Travel x to the left, bop, and then x to the right, pow. Combining these two pictures together, we get a clear picture for both momentum and time. For momentum, it's traveling mv forward and mv backwards. The negative is simply indicative of direction, which adds up to be 2mv. And to find the time, let's use distance over rate. So our change in time is 2x as our distance, and velocity is our rate. So our really change of time is 2x over v. How do we use this? We can directly use this information to calculate the force, which is the change in momentum over the change in time, which is quite obviously basic mathematics of F equals mv squared over x. Now we have one part of the pressure equation, force. For the area we gathered earlier, x squared, now let's divide the two. mv squared over x squared, the area, turns out to be mv squared over x cubed. We can rewrite this x cubed as v, standing for volume. This is our pressure for one particle, pressure P. To calculate the pressure for all the particles colliding on that wall, we need to account for the total amount of particles traveling on solely that axis. Remember the x, y, and z axes? This is where they come in. Because a wall is only affected by one axis, we need to divide the total number of particles, which we decided as n times Na, by 3, of course. However, we want to get the end product of K times the number of particles isolated. So let's move the 3 to the other side. Do you see a variable that has the mathematical potential energy, haha, funny, to translate over to become kinetic energy? I certainly do, and that's why I highlighted mv squared. Since the k of a particle is 1/2 mv squared, let's divide the whole equation by 2. Now we get 3/2 PV equals n times Na times mv squared over 2. mv squared over 2 can be interpreted as the k of a particle, as we discussed before, and when multiplying this k by the total number of particles, here we have the proof to u. U equals 3/2 PV over U equals 3/2 nRT. Wow, I know, amazing. But there's more besides the facts. U equals 3/2 PV or 3/2 nRT. Let's use U in action to derive PV equals nRT. Ironically, we have to take a step back with U in order for this to make sense. So let's go back to 3/2 PV equals n times Na times mv squared over 2. We already have two of the variables on one side already, P and V. P and V are already set for success. However, where do we go from here? So we actually have to involve a principle from the kinetic molecular theory to help us out. More specifically, we need to understand the fourth postulate of the K and T, which states that K average is directly proportional to T. Quite clearly, we have to isolate K average, whatever it means, to one side in order to set the equation proportional to T. So K average is actually the kinetic energy for 1 mole. This means the kinetic energy of one particle times Avogadro's number. Pretty self-explanatory. So understanding this concept, we can isolate the components which make up Ke per particle. Let's move n to the other side. 3/2 PV over n equals Ke average, as you can see right here. With this information, we have proven that 3/2 PV over n as a result of being equivalent to K average is directly proportional to temperature. This is where we're at. However, to ensure that 3 over 2 is not another constant and does not create further complications, we need to move the 3/2 to the other side. And once we do this, we can directly say, since PV over n is equal to 2/3 K average, PV over n is directly proportional to T. However, this just holds up in theory. What we do in experimental settings is that there needs to be a constant for then to be beyond directly proportional, to actually be equal. And this is where the constant R makes sense here. So here we have PV equals nRT. What if I said there was a much more simpler way to conceptually derive the ideal gas law? And this is a much more memorable or easy to remember way to reach the ideal gas law. Instead of going through U or momentum or finding the time and area, we can combine our knowledge of our previous laws of Boyle's law, Charles' law, and Avogadro's law to reach the same point we did with a mathematical approach. So in this conceptual derivation, I want to simply show that knowing the relationship as shown by Boyle's law, that V is inversely proportional to pressure, Charles' law, which says that volume is directly proportional with temperature, and Avogadro's law, which says that volume is directly proportional to the number of moles in the system, you can actually derive the ideal gas law. Because V is the common variable in all three laws, you can combine them and combine the 1 over P, T, and N to actually reach V is directly proportional to NT over P. And when you think about it, we're in the same situation as we were before, that to get this beyond directly proportional and actually equalize the two sides, we need to add a constant R. So once we reorganize the equation, we again once arrive as PV equals nRT. So both the conceptual and the mathematical approach are really interesting to prove this concept of the ideal gas law. I hope you will take not only parts of the mathematical side and parts of the conceptual side to truly understand what it means to use the ideal gas law and how we got there in the first place. So, of course, no presentation or no good presentation can end without a meme. So, thank you very much for listening to me today, and I hope you enjoy the rest of block days. And here are my sources. I use Khan Academy and the textbook section 5.6.